Morning, everybody, and welcome back to Internet Network Expert Service Provider CCIE Advanced Technologies class. This morning, we're going to be talking about MPLS VPNs. Okay, now the first thing we're going to talk about here real quick is the traditional VPN models, some of the design problems that they have, and then how MPLS VPNs are going to go ahead and improve some of the original designs for VPNs. Okay, now a virtual private network simply means a private connection between different endpoints of the network. It doesn't necessarily mean a physical connection. It can be over any type of logical media. So a layer 2 VPN, for example, could be an Ethernet VLAN or a frame relay network, ATM PVCs. So any type of network where it's not publicly accessible to everyone in the rest of the network. So in the case of frame relay or ATM, it's virtual because by the provider provisioning ATM virtual circuits or frame relay DLCs, we're creating a connection between two endpoints in the network. And unless other devices are provisioned into that frame relay PVC mesh or ATM PVC mesh, they're not going to be able to talk to the rest of the endpoints of the network. Okay, so the same principle with like layer 3 VPNs, which would be like with GRE tunnels, IPsec tunnels, or in the case that we're going to focus on today, which is going to be layer 3 MPLS VPNs. Now, traditionally, there's two different models that we have for VPNs. They're called the overlay model and the peer-to-peer model. Now, what the overlay VPN model is something like a frame relay PVC, an ATM VC, or a leased line. It's when the service provider is not participating in the customer's topology at all. They're providing just transparent transport across their network. Now, one of the design problems with an overlay VPN model is that it doesn't scale very well because as the number of connections are added to the customer network, you're going to need a full mesh of manually specified or manually provisioned tunnels in the service provider network in order to get connectivity. Now, there are some workarounds for this, like hub and spoke frame relay or hub and spoke ATM or ATM SVCs. But generally, you still have that scalability issue where it's going to be a lot of manual provisioning in order to get new customer sites added to the overlay VPN. And now, one of the advantages of an overlay VPN is since the customer is not participating in routing with the provider, it doesn't matter what addressing scheme they're using. Okay, so if you have a private frame relay network, you can go ahead and use RFC 1918 address space, which would be the 10 network or the 192.168 network. Or technically, you could actually use someone else's randomly chosen publicly routable address space. Okay, and some bad network designs you'll see in the enterprise, people will just randomly choose an address block and then go ahead and assign that to their network. Okay, so as long as it's a private network, that's not going to be a problem. But if you try to route out to the internet and actually reach that destination, then you would have a problem. Now, the next design we have here is called the peer-to-peer model. This is where the service provider is participating in the customer network routing. Okay, so it doesn't need static provisioning because based on routing information, you're going to be providing transport between the customer sites. So let's say, for example, we have a customer or a service provider that is running RIP version 2 in their core. If we wanted to provide a very basic VPN connection between customer sites, we could say, I want to receive customer routes from site 1 and configure a distribute list out on customer site 2 to make sure only those prefixes are advertised out. Okay, likewise, as we were receiving traffic from the customers, we would have to do some type of filtering, whether it's accessless filtering or route filtering, to make sure that traffic would not leak between customer sites. Some of the disadvantages of this is that we'd have to configure a very complex manual filtering policy on every connection from the service provider to the customer network. Additionally, the customers are going to have to use publicly routable address space, or at least unique address space within the service provider network, to make sure that they're not overlapping in the service provider's routing advertisements. Another disadvantage of this, the customers won't be able to use default routing because the service provider wouldn't be able to tell the difference between different default routes on different customer sites. And what we're going to see today with MPLS VPNs, it's going to take the best of both worlds, basically, and put them together, which is going to allow us to have flexible addressing in the customers. We don't need to use any manual filters. Okay, the filtering process is going to be automatic. We don't need to do manual distribute lists or access lists as traffic is received from the customers, but provisioning is going to be a very simple process. Okay, assuming that our underlying BGP network and our underlying IGP network are functioning properly, provisioning is going to be pretty much straightforward for MPLS VPNs. Okay, so we don't necessarily need to reconfigure every other site in the network as long as the routes are properly propagated through BGP, and we'll talk about that in a little bit here. Okay, additionally, customers can use default routing if they want to, because effectively their routing space is going to be completely separate from all of the customers. Now, the main tool in the iOS that is going to enable us to use the MPLS VPN functionality is a feature known as a virtual routing and forwarding instance, or a VRF. Okay, what a VRF simply is basically a logical instance of the routing table inside of the iOS. So if we have different customers in different VRFs, they're essentially going to have different routing tables. Okay, now when we configure a VRF configuration that is not related to MPLS and that is not related to BGP, it's called VRF Lite. Okay, you'll also see it sometimes called multi-VRF or multi-VRF CE. It's basically referring to any VRF configuration where you do not have BGP or MPLS involved. Okay, so VRFs don't necessarily relate directly to MPLS, but they are going to enable us to keep track of different routing tables inside the MPLS network. Okay, now, in order to do this configuration in global config, we're going to say IPVRF and then specify a name. Okay, the name is only going to be locally significant, so we don't have to necessarily match this up between the sites. Okay, then we specify a route distinguisher. This is going to make advertisements inside that VRF unique. Okay, and when we look at the MPLS application of this, we'll see how the route descriptor, or excuse me, the route distinguisher in BGP is going to become significant. Okay, so we create the VRF, we give it a route distinguisher, then we apply it onto the interface with the IPVRF forwarding command on the interface. And now when you issue this command on the interface, keep in mind that it is going to remove any IP addresses that you have assigned to the interface. Okay, now in the CCI Lab environment, if you go ahead and apply a VRF to an interface and you didn't know what IP address was there in the first place, that could cause you some problems. Okay, so make sure before you apply a VRF to the interface, you look at what the configuration is, so that if you need to apply, or when you need to reapply the IP address, because it is going to remove it, you know what address was originally there. Okay, there's a question here. So VRF Lite basically means configuration set of a VRF. VRF Lite basically means, we'll take a look at the difference. When BGP is involved and when MPLS is involved, it's no longer called VRF Lite. When we have just the VRF with just a route distinguisher and we have it applied to the interface, just these 3 steps, that is called VRF Lite. Okay, now what the VRF is basically doing is creating a separate instance of the routing table inside of the router. Now addresses inside the different VRF tables can overlap because they are effectively different routing instances inside the router. Okay, so it's like you have different physical routers attached to each customer, and then you're tying them all together inside the MPLS network. Now interfaces that are not in a VRF are in the global routing table. So you're still going to have your regular instance of the routing table. That's going to be called the global table. And everything else is going to have the routes in their own VRF. Okay, the default behavior that we're going to see is that routes or hosts in one VRF are not going to be able to talk to devices in another VRF or in the global table. And that's how we're going to keep them separately, or that's how we're going to keep the traffic separate between the devices. Now, one of the new things that we're going to have to get familiar with here whenever we're dealing with VRFs, a lot of our basic commands in the iOS are going to change to be VRF-aware commands. Okay, so if we have, for example, we have the ping command, you're going to have to get used to saying ping VRF. Okay, it can be very frustrating when you're trying to do basic connectivity testing and you can't understand why you don't have connectivity between two directly connected devices. Okay, one of the problems you could run into is that when you're issuing the ping command, you're not listing the VRF that the interface is in. Okay, and on the customer side, you could do a normal ping and it would be fine because they are not participating in the VRF. Okay, typically what we're going to see is that only the service provider network is going to participate in the VRF. It's going to be transparent to the customer end of the network. Okay, so let's go ahead and look at a basic example of some VRF configuration here. We have router 2 and router 4 connected over two different interfaces. Okay, this is Ethernet, so what we're going to do here, we're going to configure these as Ethernet trunks with the switches, and then we're going to configure two different sub-interfaces on two different VRFs between the neighbors. Okay, so let's go ahead and bring up the command line here. Okay, so the first thing we're going to do here, let's go over to the switch that is attached to these neighbors, and we're going to configure it as a trunk link to do router on a stick between these two neighbors. Okay, so this is going to be interface Fast Ethernet 2 and Fast Ethernet 4. Okay, so we'll reset those configurations, and on interface, we'll say interface range Fast Ethernet 2 and 4. We want this to be a trunk, so switch port trunk, we'll say our encapsulation is .1Q, and the mode is trunk. Okay, then we're going to use two different VLANs. We're going to use VLAN 24 and VLAN 42. The router 2 is going to have two different sub-interfaces here. We'll say Fast Ethernet 1/0.24 is going to be 150.1, 24.2. We'll say encapsulation .1Q 24. And then subinterface .42 will be the other subnet. Okay, there's a couple questions here. Is there any reason for removing the IP address of the interface? And like Brian Dennis said, once you apply the VRF, you are moving the interface from the global routing table into the VRF routing table. Okay, so what we see here on router 2, if we say do show IP route connected, we see those two sub-interfaces. We see Fast Ethernet 1/0.24 and Fast Ethernet 1/0.42. These are in the global routing table. Okay, the global routing table is simply the routing table you normally see without issuing any VRF-aware commands. Okay, so up until now, every time we're referencing the routing table, we are referencing the global instance of the routing table in the iOS. Okay, so on router 4, let's go ahead and configure these same sub-interfaces. Okay, so at this point, assuming that these trunk links are working with the switches, then we should have connectivity between router 4 and router 2 here. So 24.2 we should have connectivity to, which we do, and then 42.2. Okay, so again, if we look at the show IP route connected output on router 4, we can see that these two sub-interfaces, Ethernet 0/0.24 and Ethernet 0/0.42, they're both in the global routing table. Okay, so what we're going to do now, we'll add a couple loopback interfaces here on both devices. Then we're going to put one of the Ethernets in a VRF along with one of the loopbacks. Then we're going to put the other interface in a second VRF with that second loopback. Okay, so we'll say here interface loopback 24, we'll say IP address 150.1.24.4. Actually, let's say 124 /32. Then loopback 42 will be 150.1.142.4 /32. Okay, so we have our two Ethernets there and our two loopback interfaces. Let me shut down these other interfaces. We'll shut down the ATM. Then we'll shut down. Actually, let's leave the ATM up so we can see the difference between the global table and the VRFs tables here. Okay, so now that we have our interfaces assigned, we'll go ahead and create our VRFs. We'll say IP VRF. We're going to give this one a name. We'll say this is 24. Okay, it can be a name or number, whatever you configure on the link there. Okay, we'll give it a route distinguisher, and we'll go into this in more detail when we look at BGP with MPLS VPNs. In this case, we'll just say that it is. We'll say it is 124. Okay, we'll talk more information about the format and how this is going to work with BGP. And then we'll create a second VRF, IPVRF 42. We'll say the route distinguisher is 142. And now on these interfaces, let's say show run interface, fast Ethernet 1/0.24. We'll go to this interface and say IPVRF forwarding 24. Okay, 24 is the VRF name. It says now it's removing the IP address due to this interface being put into the VRF. So if we look at the running configuration on the interface, we can see it doesn't have the IP address anymore. Okay, so again, make sure that you check what your addressing is before you enable the VRF on the interface, because if there's an IP address on there, you're just going to have to go put it back in on the interface. You're going to have to reapply it. Okay, we'll do the same thing on the loopback here. So on loopback 24, we'll say IPVRF forwarding 24. Then we'll reapply our IP address. And the same thing on the other fast Ethernet subinterface and the other loopback. IPVRF forwarding 42, and we'll put our IP address back. And the same thing on the loopback. 150.1, 142.2. Now, if we look at the routing table on router 2 here, if we say show IP route connected, what we're going to see is that the global table now only contains the ATM interface and the loopback interface. Okay, if we scroll back up here a little bit, we can see when we looked at the routing table on router 2 previously, it showed the loopback 0, the ATM interface, those two sub-interfaces, the fast Ethernet sub-interfaces, plus those two additional loopbacks. Okay, at this point, every interface was in the global routing table. That is going to be the default process on all of the routers. So we defined the VRF, we applied it to the interface. Now when we look at the global routing table, we can see that only the ATM and the loopback are in the global table. Okay, to look at the other tables, we're going to look at the show IP route VRF output. So in this case, we want to look at the instance for VRF24. And for VRF24, we can see this is routing table number 24. Actually, the name is 24 of the VRF. And this contains the first fast Ethernet subinterface along with loopback 24. If we look at show IP route VRF42, we should see the other subinterface along with the other loopback address, which we do. Go ahead and do the same configuration on the other side, then we'll go ahead and test connectivity between these neighbors. Okay, so we'll use the same VRF configuration on router 2 and router 4. Now again, this is only locally significant, but just to make it a little bit clearer, we're going to use the same configuration on both sides. Okay, so we have VRF 24 and 42. Say show run interface Ethernet 00.24 and loopback 24. And we're going to apply VRF 24 to both of these interfaces. So we say IP VRF forwarding 24. Put our IP address back. IP VRF forwarding 24, and then reapply the IP address. Now, if you did by chance happen to make a mistake in the exam and put the VRF on the interface without checking the IP address, assuming that you had already saved your configuration, you could always say show startup config to see what the previously saved instance of it is. If it is a general rule, make sure you look at the running configuration on the interface before you apply the VRF. Okay, now we'll look at the other Ethernet subinterface, .42. And loopback 42. And we'll say on Ethernet 0042, IP VRF forwarding 42. And the same on the loopback. Okay, now if we look at the show IP route VRF asterisk output, that's going to show us the output from all tables. So first it's going to list the global table, followed by the individual VRFs. Okay, so depending on how many VRF instances you have on the routers, it may be easier just to look at all instances at once, or if you want just a specific table, you can go ahead and issue that command. We could say show IP route VRF 24 or show IP route VRF 42. Okay, if the VRF names are very long, it can be a little bit simpler just to say look at all the routing tables and then just go ahead and filter it out from there. So in this case, table 24, we see has the first Ethernet and the first loopback. And VRF 42 has the second Ethernet, doesn't have the second loopback. Let's see, interface loopback 42. Should be IP VRF forwarding 42. Okay, so when you are building your network with the VRFs, I would recommend that you take a basic look at the routing table like we're doing here to make sure the correct interfaces are installed before you go ahead and try to run any routing protocols or any type of ping test or any connectivity test between the devices. Okay, so if we went ahead and started pinging, trying to get reachability to that loopback, that would have been wasted time in troubleshooting. Okay, but by looking at what is in the VRF table to begin with, we can see that loopback 42 wasn't correctly installed in the VRF, so I probably put the command on the wrong interface there. Okay, now what we're going to do is go ahead and run some routing protocols between these two neighbors. But if we, actually first, let's go ahead and test basic connectivity. We'll say ping 150.1.24.2. Okay, we saw previously we did have connectivity between these two neighbors. Now when we go ahead and issue this command, what the router is doing is performing its routing lookup in the global routing table. So first off, it's saying show IP route 150.1.24.2. And we can see we do not have a route to this destination in the routing table. What we do have is a route to this destination in the VRF24 instance of the routing table. So when we send traffic to this destination, we need to tell it to do our routing lookup inside VRF24 for this destination. And we can see now we have connectivity. Likewise for VRF42 to reach 150.1.42.2. Okay, so the majority of basic testing commands in the iOS are VRF aware. So things like traceroute inside of VRF. You can do telnet /VRF. So just keep in mind, once you implement the VRFs on the interface, any normal command that you issue is going to be referencing the global routing table and not referencing the VRF table. Okay, same with the IP routing lookup. When we say show IP route, we're looking at the global table. If we want to see the individual VRF instance, we're going to have to say show IP route for that specific VRF, or show IP route VRF. Okay, so at this point, the configuration we did by creating the VRF, applying it to the interfaces, this is what is known as VRF Lite. Okay, so this is the basic configuration that we need for VRF Lite between the neighbors. Okay, now this question. So in yesterday's example with MPLS, we did not configure a multi-protocol BGP. Okay, we configured just a regular unicast BGP instance between the neighbors. Okay, now there is going to be a difference between regular BGP, VRF-aware BGP, and multi-protocol BGP. Okay, we'll talk about VRF-aware BGP here as it relates directly to the VRFs, but multi-protocol BGP with the VPN v4 address family, that is going to relate directly to MPLS. So now that we have these interfaces in the different VRF tables, they're outside of the global table, in order to get routing information to pass across these interfaces, we're going to have to be running VRF-aware routing protocols. So for RIP version 2, for example, we're going to need to tell it what VRF instance do you want to run this protocol on. Okay, so we can do this with static routing. We can say IP route inside this particular VRF. We can do it with the IGPs, which are RIP, EHRP, and OSPF. Okay, IS to IS, even though it's listed on the blueprint as a PE to CE protocol, it's only supported in the newest versions of 12.0S. Okay, so it wouldn't be covered as a PE to CE protocol, but we could see it inside the provider network core, like we configured yesterday. Okay, we can also use VRF-aware BGP, and we can do policy routing as well. Okay, policy routing, I believe, is only supported in the newest 12.0S versions as well. Okay, you'd have to double check the feature navigator for that. Okay, so let's go ahead. First off, let's do some basic static routing inside of the VRFs in order to get reachability between these links here. Okay, so on router 2, what we're going to say is that in order to reach the 150.1, 124.4 link, we're going to be sending the traffic out VRF24. Okay, we're doing the lookup inside VRF24, and it's going to go to this next hop value, which is 150.1.24.4. Likewise, in order to reach the other loopback 150.1, 142.4, we're going to say this is reachable out VRF42 by 150.1.42.4. Okay, so there's a question here. So VRF Lite does not require multi-protocol BGP. That is correct. Once we start to involve multi-protocol BGP, then it is going to be relating to an MPLS VPN. Okay, VRFs do not directly relate to MPLS, but they are used inside MPLS to keep routing information into separate tables. Okay, the VRF process itself is used just to move interfaces into separate routing tables. It's multi-protocol BGP that is going to enable MPLS to keep track of those different routing tables. But at this point, the only thing we're doing is creating a VRF and applying it to the interface. So this is known as VRF or multi-VRF CE. Okay, they're both referring to the same configuration here, which is basically VRFs without BGP, without multi-protocol BGP. Okay, so in global config on router 2 here, we're going to say in order to get to 150.1, 142.2, or 124.4, we need to do this lookup inside VRF24. We'll say this is a host route. And it is reachable via the next hop, 150.1.24.4. Okay, then we'll have the other route as well. 142.4, reachable via VRF42. Okay, so if we look at our routing tables here, we'll say do show IP route VRF24. We see we have those two connected interfaces plus a static route that says to reach router 4's loopback, use 150.1.24.4. Now, if we do the route recursion process, if we say show IP route VRF40 or VRF24, 150.1.124.4, it says it's reachable via 150.1.24.4, which is directly connected out faster than at 1/0.24. Okay, so just like a normal routing lookup in the global table, we're looking at what is the final destination, what is the next hop for it. Then we need to do a recursive routing lookup on the next hop to get it to point out a particular interface. So now on router 2 here, if we say ping inside VRF24, we want to reach the destination 150.1.124.4. And we see we do have connectivity. Okay, that's the first loopback of router 4. Now inside the other VRF, we should have reachability to the other loopback, which we do. Okay, if we try reaching this inside of the global table, we see we don't have reachability because this route only exists inside the routing table instance for VRF42. Okay, so in this case, we're not involving BGP at all. The only thing that we're doing is we have the VRFs applied to the interfaces. So let's say show run interface Ethernet 00 dot, or this is fast Ethernet 10.24, loopback 24, and show run include IP route VRF 24. Okay, so we have VRF Lite that is applying to the interfaces. Then we have VRF Aware Static Routing that is allowing us to do the lookup onto Router 4's loopback inside this particular VRF. Okay, the next thing we're going to take a look at is running RIP inside the VRFs. Okay, with RIP, we're going to be using an address family type configuration that you should be familiar with if you've dealt with IP version 6 before. Okay, so we're saying inside the VRFs, but multi-protocol BGP with the VPN v4 address family, that is going to relate directly to MPLS. Okay, so now that we have these interfaces in the different VRF tables, they're outside of the global table, in order to get routing information to pass across these interfaces, we're going to have to be running VRF-aware routing protocols. So for RIP version 2, for example, we're going to need to tell it what VRF instance do you want to run this protocol on. Okay, so we can do this with static routing. We can say IP route inside this particular VRF. We can do it with the IGPs, which are RIP, EIGRP, and OSPF. Okay, IS to IS, even though it's listed on the blueprint as a PE to CE protocol, it's only supported in the newest versions of 12.0s. Okay, so it wouldn't be covered as a PE to CE protocol, but we could see it inside the provider network core, like we configured yesterday. Okay, we can also use VRF-aware BGP, and we can do policy routing as well. Okay, policy routing, I believe, is only supported in the newest 12.0s versions as well. Okay, you'd have to double check the feature navigator for that. Okay, so let's go ahead. First off, let's do some basic static routing inside of the VRFs in order to get reachability between these links here. Okay, so on router 2, what we're going to say is that in order to reach the 150.1, 124.4 link, we're going to be sending the traffic out VRF24. Okay, we're doing the lookup inside VRF24, and it's going to go to this next hop value, which is 150.1.24.4. Likewise, in order to reach the other loopback 150.1, 142.4, we're going to say this is reachable out VRF42 by 150.1.42.4. Okay, so there's a question here. So VRF Lite does not require multi-protocol BGP. That is correct. Once we start to involve multi-protocol BGP, then it is going to be relating to an MPLS VPN. Okay, VRFs do not directly relate to MPLS, but they are used inside MPLS to keep routing information into separate tables. Okay, the VRF process itself is used just to move interfaces into separate routing tables. It's multi-protocol BGP that is going to enable MPLS to keep track of those different routing tables. But at this point, the only thing we're doing is creating a VRF and applying it to the interface. Okay, the next thing we're going to take a look at is running RIP inside the VRFs. Okay, with RIP, we're going to be using an address family type configuration that you should be familiar with if you've dealt with IP version 6 before. Okay, so we're saying inside the RIP process, we are running an individual instance of RIP that specifically corresponds to VRF1 in this case. Okay, the name is VRF1 of the VRF. So we're saying when we issue the network statement 10.0.0.0, it is only being sent out, so updates are only being sent out, interfaces in VRF1 that have this subnet applied to it. Okay, so anything in the 10 network, we're going to be sending RIP updates out that link. So for every VRF instance that we have, we're going to have a separate instance of the RIP process that is listing that individual VRF. Okay, now in our case, the major network is going to be 150.1 in each case. Okay, so we're going to have the same network statement, 150.1.0.0, in each of the RIP tables. But since they are in different VRFs, the routing advertisements are not going to leak between the different neighbors. Okay, so let's get rid of these static routes that we have on router 2. So let's say show IP route, or show run include IP route VRF. Then we'll get rid of these two. And now we're going to run two separate instances of the RIP process. So we'll say router RIP. We're going to be running a VRF instance of RIP for VRF number 24. Now inside VRF 24, we're going to be running version 2 of RIP. We don't want to do automatic summarization. And the network for the interfaces, so the interfaces are going to be in the network 150.1.0.0. They're all subnets of that. Okay, likewise for VRF 42. Configuration is going to be the same here. We're running version 2. No auto summary, network 150.1.0.0. Okay, we'll go ahead and do this identical configuration on router 4. Okay, so if we look at our routing tables here, we'll say show IP route VRF 24. We can see we have a RIP route for the first loopback of router 2. If we look at the second VRF table, if we say show IP route VRF 42, we have the route for the second loopback of router 2. Okay, but notice what happened. Even though these are overlapping inside the same major network, so everything is a subnet of 150.1.0.0/16. This is the major network. So even though the network statements are overlapping, they're still unique routing advertisements because the individual updates are only being sent out the interfaces in that particular VRF. Okay, so if we look at the debug IP RIP output here, and let's make sure logging to the console is on. Let's say show log. The console logging is on. Okay, we can see that two different updates were sent out. We're sending a version 2 update to our RIP version 2 multicast address, 224.0.0.9. We sent it out Ethernet 0/0.42. This is VRF42. That included the update 150.1.142.4. It did not include the update for 150.1.124.4 because that was in a different VRF. Okay, we can see that the top entry, we're sending the update out Ethernet 0/0.24, and it is including only the advertisement for the other interface that is in that VRF. Okay, the topology we're using for today's class is the same as the one yesterday. So in the notes box, you can see the link to the PDF there. So if you downloaded it yesterday, it's the same one that we're going to be using for today. Okay, so VRF aware RIP, pretty straightforward here. We're just creating the different VRF address families under the RIP process and then issuing the network statement based on the whatever interfaces are assigned to that VRF. Okay, next option we have is VRF aware EIGRP, basically the same type of configuration. Okay, we create the VRFs, put the interfaces in the VRFs, then under EIGRP, we're creating separate address families on a per VRF basis. Okay, so separate address families on a per VRF basis, and then we're issuing our network statements. Okay, one of the differences here between VRF aware RIP and EIGRP is that we need to specify the individual autonomous system for the VRF instances. Okay, each VRF needs to be in a different EIGRP autonomous system. Okay, when we do this, we need to initialize the global EIGRP process. So we're going to have to use some arbitrary EIGRP autonomous system in order to go ahead and initialize the process. In this case, we use whatever the maximum number was, 65535. It could be any arbitrary number that you choose. Okay, but in order to initialize the global EIGRP process, you have to choose an autonomous system. Then inside the VRF, you specify which autonomous system is this particular VRF in. Okay, so as we can imagine, the limitation of running EIGRP aware or VRF aware EIGRP is going to be based on the number of possible autonomous systems. Okay, so we would have 1 to 65535 as the number of possible instances. Okay, so it's unlikely that we're going to have 65,000 VRF instances on that particular device. Okay, and it's going to depend on the individual platform how many VRF instances that the particular device can support. Okay, now inside there's a question here, is the EIGRP AS number locally significant or does it have to be the same? Okay, inside the VRFs, now in this case, we're only looking at VRF Lite. Okay, everyone inside the VRF Lite network, and let me skip forward here a little bit. Okay, the disadvantage of using VRF Lite is that everyone must be directly connected. Okay, so when we're doing VRF Lite, this is only between directly connected neighbors. When we start to look at a situation where the neighbors are not directly connected, that's where MPLS is going to come into play, and we're going to use multi-protocol BGP to exchange the information between them. Okay, when we're dealing with devices that are directly connected, so if we're running EIGRP between router 2 and router 4 here, in that individual VRF, they're going to have to agree on what the autonomous system number is. Okay, so let's go back to the command line here, and we'll get rid of our RIP configuration, and we'll go ahead and replace this with EIGRP. So no router RIP. Actually, first off, let's test connectivity. We'll say ping inside VRF24. We're trying to reach 150.1, 124.2. Okay, we see we do have reachability to that because when we say inside VRF24, how do I get to 150.1, 124.2? We learned this via RIP, and it's reachable out that particular subinterface. Okay, this subinterface is inside VRF24. Okay, so let's go ahead and get rid of the RIP process here. No router RIP. And we're going to replace this with EdgeRP. Okay, so globally we'll say router EdgeRP1, but inside the global instance EdgeRP1, we want to run VRF instances. Okay, so if we were running EdgeRP in the global table, this would be the global autonomous system number. Okay, so keep that in mind with your design of the network. If you were dealing with this in the CCI lab exam, what you would want to look at is, am I running a global instance of EdgeRP? If so, when I initialize the EdgeRP process first, I need to make sure that I'm using the correct autonomous system number. Okay, because otherwise you would have to delete your entire configuration and then go back to change the global autonomous system number for EdgeRP. Okay, so inside here we're going to say we want to run an address family instance. This is going to be for IP version 4, and the VRF number is 24. Okay, we'll say no auto summary. The network is 150.1.0.0. And as we should be familiar with inside EdgeRP, if we wanted to, we could go ahead and use the wildcard mask to choose the specific interfaces that we want to run EdgeRP on. In this case, we're saying inside VRF24, just run EdgeRP on any interface that starts with 150.1. Okay, then for VRF instance 24, actually no, we need to say the autonomous system as well. Okay, our autonomous system number we'll say is 24 here. Inside VRF instance 42 will be an autonomous system 42, no auto summary, and network 150.1.0.0. Okay, so we'll take the EdgeRP process on router 2 here, and we'll go ahead and paste the same configuration onto router 4. Okay, now we can see we have two different adjacencies that came up, one on VRF24's interface and one on VRF42. So if we look at the show IP EdgeRP neighbor output, we can see for globally for process 1, we do not have any neighbors. But if we say show IP EdgeRP for VRF24, we do have the neighbor inside the VRF24 instance of EdgeRP. And likewise, we should have a neighbor inside VRF instance 42. Okay, if we look at the routing tables here, if we say show IP route VRF24, we see we have the EdgeRP route to router 2's first loopback. And then inside VRF table 42, we have the route via EdgeRP to the other loopback. Okay, so we can see EdgeRP here is behaving the same as RIP. We're only sending updates out the particular VRF interface based on the VRF instance configuration under the address family. So when we looked at the EdgeRP neighbors, we saw that we were forming one adjacency for VRF24, then we were forming a separate adjacency for VRF42. Okay, the routes in these individual VRF instances, they cannot pass between each other. So traffic inside VRF24 is effectively virtually separated from traffic inside VRF42. Okay, so this is a basic example of a virtual private network where the traffic cannot cross between the VRF boundaries. Okay, so no matter what type of traffic we're sending in there, it's not going to be moving between the VRF tables. And it's simply based on the principle of the routing lookup. So if we're inside VRF42, there's no way that we can get to 150.1.124.2 we can't get to 150.1.124.2 because we simply don't have the route installed in the routing table. Okay, so any traffic that comes in that's trying to leak to a different VRF, it's not going to happen because it's based on the routing information. Okay, we don't need to do any manual access list filtering. We don't need to do any distribute list filtering. This is automatically taken care of because they're separate routing table instances. Okay, the next option we have here is VRF aware OSPF. Now this is a little bit different than EDGE-RP and RIP because we are going to be running a separate OSPF process per VRF. Okay, the processes are going to be related to the particular VRF, but we don't issue the address family configuration under the main OSPF process. Okay, so in this case, we have two different VRFs. We have VRF1 and VRF2. VRF1 is running on the Ethernet, while VRF2 is running on the serial interface. OSPF process 1 is running on Fast Ethernet 1, where OSPF process 2 is running on serial 2. Okay, this is based on the fact that when we initialize the OSPF process, we're choosing which VRF it's going to specifically correspond to. Okay, so let's go ahead and take EDGE-RP off of the routers here. So no router EDGE-RP1. And we can see taking the global EDGE-RP process 1 off is going to remove all of the individual VRF instances. Okay, so be very careful of that when you do it in the exam. If you remove the global process, it's going to remove all of your VRF instances. So make sure you're always constantly saving your configuration. If you make a mistake like that, then you can always look at the startup configuration and go ahead and paste the stuff back in. Okay, also, if you remove the VRF, so if you delete the VRF, it's going to remove it from all of the interfaces. It's also going to remove the individual routing processes. Because if VRF24 does not exist, you cannot have an EDGE-RP instance for VRF24 because that routing table doesn't exist. Okay, so if you accidentally delete the VRF, it's going to delete all the configuration related to the VRF. Okay, so make sure to constantly save your configuration because that could cause you a huge loss of time, possibly something that you can't even recover from in the exam. Okay, so with OSPF, we're going to run two different processes here. We'll run OSPF 24 and OSPF 42. Okay, now the actual process ID is only locally significant still. Okay, so we could say router OSPF 1234 is for VRF 24. Okay, the process ID is only locally significant. Now inside VRF 24, we want to run OSPF on 150.1.0.0, 0.0, 255, 255. We'll say those interfaces are in area 0. Okay, then we'll have a separate instance for VRF 42 that has the same network statement. Okay, so those interfaces in the VRF are going to be in area 0. And now since we're running this over Ethernet, the timers are going to be pretty slow here. It's going to take about 30 seconds or so to establish adjacency. Just like a regular OSPF process, a VRF process, you can go ahead and manipulate any of the options on the interface. We could change the hello timers. We could change the dead timer. We could change the cost. So we could do authentication. Basically, any feature that is in global OSPF, you can apply that on a per VRF basis. Okay, so we see the first instance is up, and there the second instance is up, the adjacencies. Okay, so if we say show IP OSPF neighbors, in this case, it's showing that we have two different adjacencies. Okay, there's a question here, does that include it in the network types as well? Yes. Okay, so if we wanted to, in this case, since there's only two neighbors, we could have gone to the interface and said IP OSPF network point to point. Or if it was multi-point, we could say IP OSPF network point to multi-point. Okay, so any of the global OSPF options, you can apply those to the VRF instances. Okay, now in this case, it's showing the two neighbors, but technically they're not inside the same process. So if we said show IP OSPF 24 neighbors, we can see that those neighbors correspond specifically to OSPF 24, and that other neighbor corresponds specifically to OSPF 42. Now if we look in the global routing table, we see we do not have any OSPF information. If we look inside the VRF tables, we see we have the route to router 2's first loopback, and then in the second VRF, we have the route to the other loopback. Okay, so just like RIP and EIGRP, OSPF is keeping the information in the VRF separate. Okay, this is not necessarily the functionality based on the IGP. It's based on the fact that the router is separating the routing tables into the different logical virtual routing and forwarding instances. Okay, so packets that are going out an interface in VRF 24 cannot go out an interface that are in VRF 42. Okay, so by default, these VRF instances cannot talk to each other. We will look at later when we look at internet access solutions for MPLS VPNs, there are some ways that we can force traffic to leak between the VRFs. And like Brian Dennis was saying earlier, it's basically a hack that we can do with some routing configuration in order to get the traffic to be separate. Okay, so these are the IGPs that we're going to be dealing with when we're looking at the PE to CE routing protocols. Okay, so when we do PE to CE routing with MPLS VPNs, these are the different protocols we're going to be dealing with. So we can do static routing, we can do RIP version 2. Technically, we could use RIP version 1 if you wanted to, but you're really not going to see that. We use static routing, RIP version 2, EIGRP, OSPF. Then we can also run VRF aware BGP. A VRF aware BGP does not relate to the VPN version 4 address family inside BGP. Okay, VRF aware BGP does not directly relate to MPLS. Okay, just like the other VRF aware IGPs, they do not directly relate to MPLS. MPLS is only going to come into play once we enable the VPN v4 address family inside of BGP. Okay, now with the VRF aware BGP, we can simply say we have a different BGP table on a per VRF basis. So we're saying for VRF1, we want to establish these neighbors. For VRF2, we want to establish these neighbors. When we look at the BGP tables, they are going to be separate BGP tables on a per VRF basis. Okay, so separate BGP tables on a per VRF basis. So we'll go ahead and configure this between router 2 and 4, and we'll do two different BGP adjacencies. Okay, so we're actually going to have two different TCP sessions that are built. One is built inside VRF 24. The other one is going to be built inside VRF 42. Okay, so let's get rid of our OSPF processes here. no router OSPF24, no router OSPF42, no router OSPF 1, 2, 3, 4, and we saw that the process IDs were only locally significant. It's based on the specific VRF that it's involved in is going to control who it can form adjacency on what interfaces. Okay, so now we're going to go ahead and run the BGP process. So we'll say router BGP1. This is going to be our global BGP process. Now inside global BGP, we have an address family. It's going to be an IP version 4 configuration for a specific VRF. This is going to be for VRF 24. Okay, we want to establish adjacency with 150.1, 24.4. They are in AS1. You know, what we should see here when we're issuing the address family, it is not asking us for an autonomous system, a BGP and autonomous system. We can still only have one BGP AS per device. Okay, on the very high-end platforms, you can do some separate BGP autonomous systems, but for our purposes, the hardware that we're using in the SP lab, you're still only going to have one global BGP autonomous system. Okay, so you need to take this into account when you are initializing your BGP process. Anyone that is interacting with router 2 now, whether it's going to be IP version 4 unicast, whether it's going to be multicast BGP, VPN v4, or an address family related BGP, they need to reference router 2 as being inside BGP Autonomous System 1. Okay, so we're peering with router 4 there. And we'll also issue a network statement for our loopback. And then we'll have an instance of VRF42. Neighbor is 42.4. And we're going to advertise our other loopback, 150.1, 142.2. Okay, so same configuration on router 4. We're issuing the address family instance for VRF24. Inside this instance, we're going to create a neighbor relationship with router 2. We're going to advertise our loopback. And we'll have a separate instance for VRF42. Okay, so we can see our first instance for VRF24, we establish adjacency there. And inside VRF42, we have a separate adjacency. Okay, so if we say show IP BGP summary, we see we do not have any adjacencies globally under BGP. But if we say for this specific VRF, show IP BGP in this case, it's listing it under the VPN version 4 address family. We'll go into this in more detail here shortly once we get to MPLS. Okay, the majority of commands that we're going to be looking at related to MPLS and BGP are going to be under the VPN v4 address family. Okay, so most of the show commands, we're going to say show IP BGP VPN v4 and then issue our commands. Okay, we can see that we have two separate TCP relationships. We have one with 24.2, one with 42.2. So we could say show IP BGP VPN v4 for the VRF24. We see we have that neighbor. That neighbor is inside VRF24. And inside VRF42, we have the other neighbor. Okay, the first command I issued, show IP-BGP VPN all. It's saying all VRF instances. So if we look at the BGP table, if we say show IP-BGP VPN v4 VRF24, we see that is the routing table, or the BGP table, I should say, for VRF24. Then we're going to have a separate BGP table for VRF42. Okay, so there's a question here. How does BGP, multi-protocol BGP, and VRF-aware BGP keep track of the different updates? Okay, it's going to be based on this route distinguisher that is in the BGP table. And we'll take a look at this in more detail here in a second. But basically what's happening, even if we had overlapping updates inside BGP, okay, let's say on router 4 here, let's go to interface loopback 24. And if we show run interface loopback 24, we'll say our IP address here is going to be 150.1.142.4. Okay, so if we look at the show IP interface brief now, and we'll look at just the loopbacks, we can see we have these two loopbacks, but they have overlapping addressing. Okay, this is going to be okay because they're inside separate routing tables. So if a packet comes in an interface that's in VRF24 and it's going to 150.1.142.4, it knows which specific destination to send that to. If it comes in an interface in VRF42, it knows that this is the specific destination that it is looking for. Okay, if we go back to the BGP process here and we say address family IPv4 VRF 24, network 150.1.142.4, ask 255, 255, 255, 255. And then we go over to router 2, and let's say show IP-BGP VPN v4 VRF24 summary. Actually, we'll say all summary. We should be receiving one route from router 4 per VRF instance. Okay, which we are. We see inside VRF24 we have one route. Inside VRF42 we have one route. Okay, if we look at the show IP-BGP VPN v4 all, that's going to show every VRF instance in the BGP tables. What we can see is that we have the same route in multiple routing tables. So if we say show IP route VRF 24 150.1.142.4, we can see this is reachable via this next hop, 24.4. If we look inside the other VRF, VRF42, that is technically a different route. It's reachable via a different next hop. Okay, the reason why is that if we look at this specifically in the BGP table, we'll say show IP BGP VPN all 150.1.142.4. There are two different paths that we have. We have the one that is in VRF24 and the one that is in VRF42. The way that multi-protocol BGP is keeping them separate is by adding this route distinguisher onto the prefix. Okay, so the route distinguisher is what BGP uses to keep track of individual routes inside different VPN instances. Okay, this route we see here, 1:24:150.1.142.4/32, this is actually, let me go ahead and bring up the whiteboard. This here and this here, these are what is known as the VPN v4 routes. A VPN version 4 route is simply an IP version 4 prefix with a route distinguisher prepended onto the front of it. So we have the route distinguisher plus the route. And since the route distinguisher is going to be globally significant to the entire MPLS cloud, even if we have overlapping IP version 4 prefixes, it's going to be globally unique because the route distinguisher is prepended onto the front of it. Okay, so let's go ahead and take about a 10-minute break here. And then when we get back, we'll get into integrating this VRF-like configuration that we were looking at with MPLS in order to get an MPLS-based VPN.